So, today we're diving into the incredible and, well, incredibly hot world of AI infrastructure. We're going to pull back the curtain on the massive engineering challenge of keeping the brains behind AI from, literally melting down.
Think about it. Every time you use a chatbot or generate an image, you're firing up this huge, power-hungry system. So what's stopping all that computational firepower from just overheating? Well, it's this amazing story of physics, clever engineering, and some seriously advanced plumbing.
Right, so to really get the cooling problem, you first have to understand the heat problem. And it all starts at the tiniest possible scale, deep inside the GPU, which is really the workhorse of all modern AI.
So right at the heart of the GPU, you've got this thing called high bandwidth memory, or HBM. The best way to think about it is like a tiny, super fast workbench sitting right next to the main processor. Every single piece of data the AI needs has to get moved onto this workbench, worked on, and then moved off. And all that shuffling back and forth, at these insane speeds, that creates a kind of electronic friction. And you know what friction means? Heat. Lots of it.
So what's actually cluttering up this little workbench? Well, it's basically three main things. First up, you have the model weights. That's the AI's entire brain, all its knowledge. Next, the gradients, which are the signals that help the model learn new things. And finally, the activations. You can think of these as the AI's short-term memory, all the little calculations it's doing from one moment to the next. Just getting all this stuff loaded up is a huge job.
And just to give you an idea of the scale here, the weights for a pretty modest 7 billion parameter model take up around 14 gigabytes of that precious workbench space. And that's before you even start processing your data, before any of the actual learning even kicks off. And that's just the starting line for our heat problem.
Okay, so one hot chip, you can deal with that. But modern AI isn't using just one chip. No way. The problem scales up, and it scales up fast, turning a single hot component into a massive room-sized challenge.
To get these giant models trained, engineers have basically two main plays. The first is data parallelism. They make a full copy of the AI model on every single GPU, then feed each one a different chunk of the data to work on. The other way is model parallelism. This is when the model is so gigantic it won't even fit on one GPU, so they actually chop the model itself into pieces and spread it across a bunch of them. But either way, you get to the same place. You've got to pack a ton of GPUs together super tightly.
And this is what that looks like in the real world, a modern AI rack. And believe me, it's not just a stack of servers, it's this incredibly dense, interconnected system. You've got your core compute units, the DGX systems, packed with GPUs. Then you have the high-speed networking switches that weave them all together. You've got massive storage arrays constantly feeding them data. And finally, management nodes that act like the conductor of the whole orchestra.
Okay, so we've got all this hardware crammed together. But what does that actually mean for power? I mean, what are we really talking about in terms of energy? Let's put a number on it.
Over 40 kilowatts for a single server rack. Now, to put that into perspective, your average house probably uses, maybe 1.5 kilowatts? So this one cabinet is pulling the same amount of power as 30 houses. It's wild. And here's the kicker. The data centers we've built for the last 20 years, they were just not designed for this. Not even close.
And you got to remember, not every watt of that power is actually doing the AI's work. In the data center world, the big metric everyone obsesses over is called power usage effectiveness, or PUE. It's a really simple ratio. You take the total power the entire building is using, and you divide it by the power that actually makes it to the computers. A perfect score is 1.0, which would mean zero energy is wasted on things like cooling, which of course is impossible in the real world. And this slide really shows you why. For every chunk of power that goes to the useful IT stuff, you have to spend more energy on everything else. The cooling, the lights, you name it. That second bar, the overhead, that's the energy tax you have to pay just to keep the lights on and the servers from frying. And for these AI racks, that tax is huge. The whole game in modern data center design is to make that overhead bar as tiny as humanly possible.
So how in the world do you fight this much concentrated heat? I mean, you can't just point a bigger fan at it, right? The answer is to stop thinking about air altogether and to embrace something way, way more effective: liquid.
And this really breaks down into two main flavors. First, you have direct-to-chip cooling. This is like precision surgery. You run these tiny pipes of coolant into a metal block, a cold plate, and you put that block directly on top of the hottest parts of the chip. It's super targeted,
And then you've got immersion cooling, which is, well, it's exactly what it sounds like. You're going all in. You take the entire server and just sink it into a big bath of a special fluid that doesn't conduct electricity. It's the most efficient method out there.
So why go through all this trouble? Because the payoff is absolutely massive. First off, liquid is just ridiculously better at moving heat than air. We're talking up to 1,000 times better. That means huge energy savings and a way better PUE. It lets you run your chips at full blast without them slowing down to protect themselves. And because it's so good at its job, you can pack even more power into the same room, all while being greener. It's a win-win-win.
And this isn't just some abstract engineering puzzle. Like this quote points out, everyone, from small businesses to huge corporations, is racing to get in on AI. Being able to tap into this kind of super dense liquid-cooled power is becoming a massive competitive advantage. So, you see, figuring out this heat problem, that's what's actually making the AI future possible for all of us.
And that really brings us to the big final question, doesn't it? We're basically in an arms race between how much power AI needs and our ability to cool it down. For now, it seems like engineering is winning. But as these models just keep getting bigger and bigger, you have to ask yourself, is there a wall we're going to hit? A point where we just physically can't get the heat out fast enough? It's a fascinating thing to think about. Thanks for tuning in.